Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this set of video lessons, we're looking at techniques for numerically computing the value for roots of equations. And in this lesson in particular, we will be looking at the Regula Falsi method. So we are specifically looking at a cubic polynomial equation generated by the Pang-Robinson equation of state, and we are doing this for chlorine at 500 Kelvin and 150 bar. The Regula Falsi method is an improvement over the bisection method. It should converge much more quickly. In the bisection method, what I did was I looked at a value of a function. I said, okay, between a positive and negative, the curve had to cross the axis, and so therefore it had to have that zero value somewhere in there, and we just cut the interval in half. Now then what we're going to do is we're going to take a little bit of a more intellectual approach to this, and we're going to cut the interval by using a straight line fit between those 2 points. And if I use the fact that this new guess has to be on the line between those 2 endpoints, and I will guess that it should be close to where the function or the straight line crosses zero, then I can use algebra and my knowledge of slopes to come up with this as my equation. Now remember our notation here. X sub n is the x value that gave a negative value to the function. So it came below the axis. X sub p is the value of x that gave a positive function, or it was an answer that was above the axis. And so x sub n minus x sub p minus x sub n times f of x sub n over f of x sub p minus f of x sub n. So what you'll see here is this is going to be essentially my slope of my line. And whichever point I use here, I'm going to evaluate that function. So this is going to be my fixed point. So I have a fixed point and a slope to figure out what the next point should be. There is something called a modified Regula Falsi method. Now I'm going to just show you the picture of what it's trying to do. I'm not holding you responsible in my class for this. But the modified Regula Falsi says, we've just got so much wasted space. Why am I going all the way to the height of the function? Let's just split the difference between the y-axis and the actual final function. And we'll use that plus my slope to get me an even closer answer. And this converges even faster. Don't worry about it. I didn't give you enough detail to make that make a lot of sense, I know. But we'll be using the Regula Falsi method. Now on this, we still want to know when to stop, and we're going to again use relative error limits. So I'm going to be looking at my x values and comparing those to determine when I'm ready to stop my computation. So let's now move to Excel. So I've set this up using exactly the same spreadsheet I've been doing, and we found from our graphical technique that these are my 2 values of z that were closest to giving me z, or this function here, equal to 0. And I guess I'm doing this for 520 Kelvin and 150 bar. Doesn't really matter. Okay. So what I'm going to do is I need to come up with my new guess. Okay. And so the technique says that I'm going to take one of the endpoints, okay, minus the difference between the 2 endpoints times the value of the function at my fixed point divided by, and then I'm going to take the difference between the functions. And I want to make sure I get the subtraction in the same order I had before. And that's going to be my new guess. And the value of the function is this, and my relative error is going to be this. And so what we can see is that, yeah, indeed, I got the error smaller than I had it before, okay? So this seems like it's going to get me there faster. And I'm just going to copy this down below. And now then, which 2 points do I want to use? Well, this had a negative, so I will use this as that point. And this had a positive, so I'll stay with it. And it really didn't change too much. Okay? So we must be getting kind of close to what we should be using. I can do this again. And again, I want to use this as my negative. I'll stay with that for my positive. And we're, it's very quickly getting down to almost no margin of error there. Okay. Yeah. Okay. Anyway, so that is the Regula Falsi method. I am getting this down. You'll see that I'm not seeing any change out many decimals. Okay, so it's probably pretty darn close. Okay. Oh, let me just point out. Okay, this relative error was done using these. You're not seeing much change because I could have done using the others. And you would notice, since that's the endpoint I'm converting every time, you'll see that I have indeed converged down to where there's very little change for each point. And so anyway, that's the Regula Falsi method. In our next lessons, you can either go next and look at the VBA, the Visual Basic, for programming the Regula Falsi method, or you can continue looking at Excel, and we will next be looking at the Newton-Raphson method. Thank you very much for your time.